So today we have several folks with us here today. So Keith Rush and also Brendan McMahon and Abradeep Thakutra. And today we'll be talking about a particular paper. So private online prefix sums via optimal matrix factorizations. Excited to hear more. I believe one of the main, one of the motivations here is thinking back to some of this recent work, trying to avoid things like sampling and shuffling to amplify the performance of privacy preserving methods like DPSGD. And in particular, thinking about one of the techniques there, this tree aggregation technique, and understanding it and refining that idea, and also kind of generalizing it and viewing it as part of a more general set of techniques. So I'm sure I did insufficient job summarizing that, but excited to hear more from everyone today. And so I'll just send it over to you, Keith.
Okay, cool. No, that was perfect. Yes, I am Keith. That's who I am. Here to talk about this paper, as Ginger mentioned, and yeah, that was pretty much exactly where it came from. So that's the first few slides. I could probably just skip them all. So that's sounds good. My talks tend to be very freewheeling. So I think Sam was saying, please post questions or whatever. Yeah, sounds great. I'm always happy to take questions in the middle and do things in a little bit more interactive way. I don't like lecturing at people because I also don't like to be lectured at. I get kind of bored and zone out. So yeah, this is joint work with Brendan and Abradeep. Oh, that's okay. That's a little bit, the delay is a little strange. Who are both here, and that's me in the middle. I think this is alphabetical order left to right, which is the way we put it in the paper as well. And that's why my name is boxed, because I'm going to be the one that's going to be talking to you today. Although Brendan and Abradeep should also feel free to jump in and correct me if I ever misspeak too much or talk too much out of turn. So I kind of want to ground like where this whole work came from, with kind of like an overarching focus that I think influences. Oh, Brendan, Abradeep, and I were all at Google, and that's why there's a Google on the slides. That probably makes sense. But we work in a team that kind of has a focus on basically a sentence like this: building core mechanisms for improved ML model training, often with differential privacy, and special emphasis on the federated regime. This is kind of like an overarching goal that I think motivates a lot of the work that happens in our team and a lot of other teams, both at Google and elsewhere. So probably there's many people in the audience. Actually, I have no idea how many people are in this. Oh, 24. I see that there. Who also kind of have similar goals. A similar focus. So this is kind of like the overarching thing that led to a lot of the work, both that predated the thing that we're talking about today, which we'll talk about a little bit in the background, and the thing that we'll talk about today itself. So, depending on how well you know all these terms, we're going to give a brief introduction to each of them in turn, and kind of how they interact together, or at least in our understanding. First, we have to start by talking about differential privacy. Depending on whether you know that too well or not, we'll give a brief introduction, slightly informal introduction. We'll talk a little bit about federated learning, but I think that this audience probably knows it pretty well, and kind of how these two things interplay. And we'll talk about how like ML model training kind of looks in this world, because I think a lot of you can do things in the federated setting with differential privacy that aren't necessarily machine learning model training. So a lot of other people on our team, and I think Brendan and Abradeep too, often work on kind of similar problems that aren't necessarily machine learning based. But machine learning is really the thing that kind of generated the work that we're going to talk about today. And then once we talk about this background, we'll talk about kind of what kind of core mechanism we ended up describing and talking about in this paper. And that's going to be kind of the technical content of the talk. So the things in red are kind of like background. The thing in green is kind of like, well, what was generated like with this focus, and yeah, that's like what's actually in the paper there. Okay, so I think, yeah, there's actually a lot of related work here. So I think, as Ginger mentioned, we're talking about kind of frame all these trade aggregation things in kind of a more general class. And this more general class was introduced in 2015, kind of called the matrix mechanism, which is basically like essentially you take a linear thing, you represent this as a matrix, you can factorize this matrix, and you do something with this factorization. We're going to talk about that a little bit more later. There's been a lot of work kind of on like the matrix mechanism itself, on optimizing various aspects of it, on analyzing the kind of errors that are achievable. Like, is matrix mechanism actually optimal with respect to all potential like differential privacy schemes that compute these like linear things. And there's this kind of parallel line of tree aggregation, which is kind of like more directly where we inherited from, because we kind of tied the tree aggregation line in to the matrix mechanism line, or at least that's how we think about kind of what we did, which was introduced by Dork et al. And concurrent work with Chan et al. In 2010, 2011, was kind of statistically refined by somebody at Harvard named James Honaker, who we've, I think, never actually talked to, but we've leveraged their work a lot. So we always say that we got to like reach out to this person. To the best of our knowledge, I think that these tree aggregation mechanisms were first shown to be compatible with adaptive streams by Adam Smith and Aberdeep in 2013. And we're going to talk a little bit about like what an adaptive stream is and why we kind of need it to do machine learning model training. That's kind of where machine learning model training fits in here. And it's an important point, I think, to notice that like tree aggregation, as I just mentioned, can be used in this adaptive streaming setting. But all of the previous work on matrix factorization really could not, because it was kind of designed to work in this kind of batch offline case. And our work really kind of focuses on investigating what that intersection is, what that interplay is between like online tree aggregation schemes that could work pretty well for a lot of problems, and kind of these matrix factorization mechanisms. Oh yeah, we are interested in computing literal optima here, which I think I'll mention later in these slides, that why these constants matter. Yeah, okay. So as I said, we're going to talk a little about differential privacy. So what is differential privacy? It was introduced in this big, important, fancy paper in 2006. I forget who all the names are, but it's Dork, McMahon, somebody, and Smith, Adam Smith, I think. I forget who the N is. So Aberdeep probably knows, probably Brendan knows.
Yeah, McSherry. Dork, McSherry, and Smith. Okay,
there you go. So Aberdeep knows who it is. There's also a link here, so you can go read the paper yourself. It kind of starts with a database D. It's got all these 5 records in it here. Yeah, you get a database of 5 records. There's some mechanism, you compute some statistic over this database. Mechanism A computes the statistic, returns you theta. A is randomized thing, really has to be randomized in differential privacy, and we'll see why. So you get some distribution. Oh, is that going slow? Okay, yeah. So you get some distribution, right? You get A of D. Yeah, distribution over outcomes, right? Because it's randomized. Okay. So kind of the key question in differential privacy, the main observation that really started the field is like, okay, well, what happens if I remove one of these records? That gives rise to the notion of a neighboring database, which is this D prime here in relation to this D, which is like symmetric difference between these two things is 1. I always forget, this is probably called the add one model of differential privacy. There's also the replace one, which is like, you swap one record for another. They're very similar. But the point is that, these two databases differ exactly 1 entry. So obviously you're going to get a different distribution here, or in general, right? You're going to get a different distribution. Of course, you don't have to get a literally different distribution. You could just ignore all the data and release some random number, but like maybe you probably don't want to do that. Differential privacy is really a statement that these two distributions are close in some sense. Yeah, that's really what it is. So I'm a mathematician by training, so I always think about like, well, first of all, I guess I don't think about probability as probability at all. I think about it as like functions. So just functions on measure space of total mass 1. So for me, we talk about like closeness of distributions. It's always like some kind of integral is behind there, but that's not, you know, the traditional definition of epsilon delta differential privacy, which is what we're going to talk about here. You know, I actually don't know how to express that in terms of integral. Maybe it can be done, but you know, there's these things like Renyi divergences that you know are related here. Okay, whatever. Closeness of distribution. That's the thing that's kind of matters, like spiritually matters. So we'll talk about, I guess, the formalism. In what sense do these things to be close? Well, it's really in this sense. This is epsilon delta. There's also epsilon. This delta kind of, you know, was introduced, I think, usually to deal with things at infinity. So if you had, you know, for example, two Gaussians at different points, you know, they decay like e to the minus x squared. So this e to the minus x squared, you take that ratio. The ratio of these two things out at infinity is blowing up at you. So that's a problem. But if you set delta to be 0 on the right-hand side here, you can kind of interpret this epsilon a little bit easier. Like take the ratio of those two probabilities. That's kind of telling you that the ratio of the density functions that represent these distributions is bounded. And that's why, I mean, that's why you need this delta to handle things at infinity. You can actually hide a lot in this delta too. And the fact you can hide a lot in this delta means that we usually want this delta to be really small, like smaller than 1 over the size of the total database you have here. That's why there's that little O of size of D inverse on the right-hand side. And epsilon usually want to be order 1. So like exactly what that means, you know, is application dependent. But notice that the dependence on epsilon is exponential. So like epsilon of 50 is like pretty big number, right? Like, I don't know exactly what that number is, but it's not small. Yeah. So the point being that the relationship between all possible observations has to kind of satisfy this bound, and that's epsilon delta differential privacy. Okay. You know that, and that's all the background that you're getting there. Now, quick background on federated learning. Federated learning, kind of this distributed setting where clients, which are these devices, which I always in my mind actually think are acting like servers, but you know that's just my particular weird twist on it. Everyone else calls them clients, so I should stick to clients probably. Collaboratively train, or really in general, okay, we're federated learning, but there's federated computing. So kind of collaboratively compute some function. In federated learning, this function is like a machine learning model. So it's like collaboratively training a machine learning model without transferring their data to any kind of like central server. So kind of the canonical first example of an algorithm in federated learning is federated averaging, which you probably all know, which is like you get some model, you stick it at the server, each client downloads a snapshot of the model at a point in time t, runs some number of local steps. Usually this is like epoch normalized, so runs let's say 1 epoch of local training, ships back the updated model to the server. Server computes some average, and then based on this average, moves its model at the next time step t+1, like somewhere. So in original federated averaging, you just literally computes the average of these things, and that's your model at time step t+1. So I think one important thing to note is that this is not the same thing as just doing like a distributed gradient descent, because you are not literally you're computing gradients in these clients, but you're taking multiple steps. So each of these clients is kind of following a curve, and then we average the result of following these curves back in the end. So then there's this like iterative procedure that takes place between the clients and the server. Server kind of like orchestrates in some sense. Then once this thing has converged, model engineer says, good, I've trained my model, great, fantastic. Like I ran some evaluation on it, it looks great. So I'm going to ship it off to all these devices, all these other devices, every device in the fleet, and deploy it. One interesting thing here is that usually, or at least at Google, we have some enormously massive number of devices we could be training on at any given time, but you don't need to like actually literally train over all of them every single iteration. Usually you're just training on a couple hundred or something. There's kind of, actually, I think that Ginger and maybe some other people who are maybe here did some interesting work maybe like a year ago on what kind of returns do you get by making these number bigger? And I don't really remember what these were, but something. That was like a large cohort training. So okay, how does this work with differential privacy? Well, like fairly naturally, there's kind of a natural composition between the system, the federated learning system, and kind of like especially central differential privacy. I'm not going to get into central versus local DP. Local is like, okay, I added the noise before I ship my data out to anyone. Central is like, I trust some central aggregator to tell, like, actually add the noise as appropriate, as correct. So okay, that's kind of a super high level difference. And we're just going to talk about the central version here. In the central version, the client has to kind of clip their update to a certain magnitude, because usually you have to add noise. Well, I mean, always, I guess, in every example that I'm aware of, you have to add noise, which is proportional, standard deviation is proportional to the sensitivity of the records that you need to protect. So like how much can changing one record in the database, doing this like symmetric difference operation we talked about earlier, affect the outcome of the function you're trying to compute. Usually you need to calibrate your noise in a way that's proportional to that, basically. So the server has to add some noise when they're combining all these average updates we were just talking about earlier, which are clipped to some ball, which, by the way, is a difficult mathematical operation to understand, like clipping. And usually most people are just like, okay, we just assume that clipping doesn't happen when they're doing analyses of DPSGD, because it's just like really hard. Like, well, what is that? But anyway, it's important to note actually that this sigma down at the bottom here, which is this like averaged client update, these are going to be these terms xi in the SQL, like when we talk about kind of the mechanism that we end up designing here. But we also really overload xi. So like we kind of think of xi as just being like scalars. And we, factorize this matrix. So our matrix is just, n by n. So it, takes whatever 1 by n. I always forget column vectors with n entries in them, right? And like multiplies them on the right-hand side. So like generally, really, you should think of this as like a more general tensor contraction, because these average model updates are like high dimensional because they represent a machine learning model, right? But it's kind of, we kind of elide that distinction left and right, because it doesn't really matter. Like the algebra is basically the same. So that this thing will be what you should think about these exercises being later, even when we're basically treating the scalars. Just a heads up that's what's going on here. Okay, so we talked about DP, we talked about federated learning, so we got to talk a little bit about how like ML works with all these things. So there's kind of two algorithms that we're going to focus on here. One is DP-SGD, which is exactly what you think it is. It's like you do SGD, you clip your gradients so that they're bounded by this L thing. We just talked about that clipping earlier. And now you add some noise at each step of SGD, which is calibrated proportional to this L. That's what DP-SGD is, right? I mean, we got this SGD update on the top. Actually, I mean, that's literally just gradient descent update, I guess, because I didn't put any randomness in there, but pretend like I did. Then we got the DP-SGD update on the bottom here, which is we clip that gradient. We sample for some noise distribution, say it's Gaussian, standard deviation, proportional to the clip for order 1 privacy loss. You can always make it higher or lower depending on what you want to do, but think about it as order L. I think that's probably just easier for everyone. Effective privacy bounds for DP-SGD, usually, and I think by usually I think maybe probably literally always, rely on something called amplification by sampling, which is like, okay, well, in SGD, you are literally sampling, right? You're sampling, batches from your big data stuck on a data center somewhere. Amplification by sampling tells you that if you're sampling these things uniformly at random, and I forget, you probably need like Poisson sampling, right? Something like that. So your batches actually can change size across round too. There's an average, whatever. if you're doing this operation, you can essentially just boost the privacy guarantee that you give because there's some kind of like extra hiddenness that's given for you. And there's people that work on, replacing this with shuffling. Okay, but point being that if you're going to try to compose this with a federated setup, this is like basically absolutely a non-starter. Like this is totally impossible for you to guarantee, because how do you have any idea how you're actually sampling from this like population of 2 billion devices? Like, is there absolutely no bias in that? Or are you literally doing it uniformly at random? That's really hard to talk about. Like that system's problem is like, I don't even know where we'd start. So kind of like that was the inspiration for Brendan, Aubrey. I think I saw Peter here. Some more people, I think Jung, I don't know if Jung's here or not. I think Shuang was working on this. I don't know, a lot of people who kind of designed this single pass algorithm, which is called DPFTRL, to essentially replace the kind of things that you need sampling to do. And it was kind of DPFTRL that also, and the analysis, the observations that came out of that kind of generated the work we're talking about here. So what kind of primitives make sense in this setting? In both DPSGD and DPFTRL, the private partial sum of gradients observed so far really plays the crucial role. And you can see this in DPSGD just by unrolling this loop, right? I mean, you know how to compute this thing up at the top. You're taking a bunch of gradient sets, you're literally just adding them up, right? So the difference between state at time t and initial state, which remember is random, so it's not private, so you don't need to really worry about the initial state thing, is just this scaled sum of all the gradients you've seen. And the DPFTRL work made the super crucial observation that, some kind of correlated noise between the steps of its procedure can give you better error because the error on the sum is more important than the error on the individual gradients. So remember that when we were talking about DPSGD earlier, we literally just add some noise to the individual gradient. It's like, it's independent across steps. But the DPFTRL work really observed that if you correlated this noise across steps, you can win, even if the average noise per step is larger. But it's correlated, so you can stay kind of closer to the model, the unnoised model during training, even though the variance, like the per gradient variance, is higher. So Brendan had some collab that generated this plot, which was in this blog post we're going to talk about in a second here. Well, the appropriate primitive then is the DP computation of these partial sums. We need to measure the error of the computation of these partial sums. That's the thing that really matters. And an important point to highlight here is that each of these algorithms, each of these model training algorithms, and I think anything that has a shot to train a machine learning model really in the modern setting, it is going to be adaptive. It's going to have some kind of adaptive streaming property so that the state at time t is going to influence the query made at time t plus 1. So this is kind of the fundamental streaming or online requirement that we have to work under to make our mechanism make any sense for this setting. So that's kind of where we go back to that focus. We want to design some core mechanism that can apply in all these settings, and this is something that we really need to make that work. How can we do this today? These are the tree-based aggregations we were talking about earlier. Well, we construct something like a binary tree. We imagine constructing this complete binary tree from all of the observations we make. So these xi's are the gradients we were looking at earlier, or the average model update in the federated setting. But now I think is the point where you can start thinking about them as just scalars. We make this complete binary tree from all of the gradients we're observing during training. We add noise that's at zi, is something sampled from a Gaussian, to every node in this tree, and we treat this entire tree as the private object. This is like the thing that's subject to release. So this is the thing that we analyze. This is the thing that kind of determines our privacy loss. It's important to note here that this tree-based aggregation scheme is asymptotically optimal, but we really care about the constants. And when I say asymptotically optimal, I mean that the asymptotic is right. This is like logarithmic error in n or which is the number of leaf nodes. So it's like the height of the tree is like the asymptotic error. But because these constants, these constants in the error here are reflected in how much noise you need to add, basically, like those constants are really, really important. Like in the differential privacy application, what the difference between whatever, like, 2 epsilon equals 2 and epsilon equals 10 is like massive, right? Because that's like e to the square versus e to the 10th. Those are like really big differences. So like what constant you have is actually an important thing for you. And how do you make these things streaming? So remember that we had these, this was our picture. The question we're going to concretize on is, when we observe x1 and x2, what can we use to estimate x1 plus x2? So kind of like the key in this correlated noise thing is to notice that this tree has kind of multiple observations in it, right? So this node, x1 plus x2 plus x3, or plus z3, sorry, is an estimate of x1 plus x2. But you can make an estimate of x1 plus x2 from these 2 bottom nodes, right, on the left-hand side too. But you also notice you can make an estimate of x1 plus x2 from the rest of the nodes on the right too. But can you use those? The answer is no, you cannot. Oh, did that not go anywhere? Maybe I duplicated that slide. We can't use these future values to reduce variance. And why is that? In the non-adaptive streaming setting, if we just had values that were coming in a stream, but there was no relationship between them, we can use this trick of pre-computing all of these ZIs and using them to like compute our reconstruction, correlating the noise between these ZIs to compute our reconstruction. But with that activity, the noise that gets added at time t influences the query you make at time t plus 1. So there's this correlation between the noise you add at time t and the private data that you're observing, which means that this kind of formalism, which is that we have, we're adding z4 in a way that's independent of x3, the value of x3, for example, that just like breaks down. We're not running the same algorithm anymore if we use any of these nodes on the right-hand side to compute our estimate for x1 plus x2. Yeah, so that's kind of like how requirement in these tree aggregation settings. So okay, this Honecker observed that there's these correlations between these things, and that you can create some kind of like maximally efficient estimator from the nodes underneath you in this tree. This is the Honecker estimator from below. So it's like literally from below. So that is compositional with the streaming setting, the online streaming setting. And you can use these 2 things together with DPFERL to totally bypass reliance on amplification by sampling. So here's some plots from the DPFERL paper. I wasn't super involved in it, so I just copied some plots that like look good. Oh, great. They look really high. Fantastic. Yeah. Okay. So this approach was leveraged to train what is, as far as we know, the first ML model with formal DP guarantees on consumer data. And the reason you need this formal guarantee, or you need DPFERL to do this formal guarantee, because it's a lot easier to implement a single pass algorithm in the infrastructure than actual literal random sampling. So there's some blog posts linked to it here by Brendan Umberdeep. So there you go, you see it done. You may be asking, where are my matrix factorizations? We haven't done that at all yet. Okay, so we're going to talk about the matrix mechanism. Remember that we wanted to compute some differentially privatized version of some map. I'm going to call this map x to sx. So s is just going to be some matrix. That's why we multiply s with some vector x, and that's the map that we get. Now we consider that we factorize. Sorry, I hit that button by accident. S into w times h. There's some intermediate dimensionality, so w is n by d, h is d by n. Under this factorization, we can imagine privatizing the vector hx instead of the vector x or the vector sx after we compute this map, and view multiplication by w as this kind of post-processing step. So it's like classical fact in differential privacy that once you have a private object, you can do anything with it. You're not going to lose the privacy anymore, which is good. That would be a pretty bad definition of privacy if you could like unprivatize something that was already privatized. That would be pretty rough to work with. So we have some, concrete notion of sensitivity that we have to add. This is really analogous to the clip that we were talking about earlier. How much noise we need to add depends on our model of adjacency. So in analogy with DPFERL, we assume that we want user level differential privacy, which is like the thing in the federated setting, essentially corresponds to the rows in the database corresponding to like a user's entire contribution instead of like a little single sentence or whatever. So that's kind of example level versus user level. Each user contributes a value within the range 0 to 1. So that's essentially your clip that you're going to have to do for every client is this one here on a single round I. It's a single pass algorithm. If X includes some contribution and X prime does not, this is kind of our notion of neighboring databases. We can bound the sensitivity of this map X to HX in terms of this quantity. And this is, this isn't just a bound. This is literally what the sensitivity is, because you can, construct a vector that's like 1 in the appropriate entry. Yeah, and this is L2 sensitivity. So this measures like how much an output of a function can change when the output is measured in L2 when you have a different, when you have a neighboring database. Okay, so this is some quantity that we have to deal with, basically. We can compute straight up in this setting the expected reconstruction error for a given privacy level. This isn't a very particularly difficult computation to do, so it's appeared multiple times in literature. And it's this L down at the bottom. We get here, it's this product between the Frobenius norm of W and this like max over column norms of H. That's another way to interpret that sensitivity. Okay, where does the binary tree fit in? Remember that what we were doing is abstractly, we're just like computing this big complete binary tree, and then we're DPifying it in the end, and then we're reconstructing. Well, I guess that's in the middle. We DPify the binary tree, and then we reconstruct in the end. Clearly, the binary tree is linear, right? Because all the nodes in that tree are sums to the leaves, which are integers of the vector here. So there is some matrix H that corresponds to this thing. So, okay, this is really easy to see. Right? There's X1. Discovering up here. Yeah, okay. There's X1. There's X2. X1 plus X2. Okay, you get where this is going. X3, X4, X3 plus X4, then all the rest. Okay, X3, X4. This is taking a long time. Finally, okay. X1 plus X2 plus X3 plus X4. These are what is going to, those are the values you would get with your vector HX if you had X1 through X4 as the argument to this matrix. So, okay. Special form of our problem, this geometry looks really nice, especially if you drop that max over column norms of H. You can very, very easily compute optimal W for a fixed H or vice versa. For a fixed H, the problem we care about is just expected, or is just written in terms of this Frobenius norm, right? Which means that you get some quadratic problem with linear constraints, so we assume that C is some linear subspace. So you can write down a closed form solution. If C is all matrices, this is literally just the Moore-Penrose pseudo inverse, or this is like whatever SW dagger or something like that. Can't remember. Oh, SH dagger, I think, is this optimal W. And if you have linear constraints C, you can write down linear constraints that correspond to the streaming constraints. You have this kind of like row by row constrained Moore-Penrose pseudo inverse, kind of a similar thing, but not that difficult. Okay, in a nice recovery, what's optimal W for a binary tree H? It's exactly what Honecker wrote in his paper, actually. So you will see that these are the right values for the Honecker estimator from below. So this is the constrained version. You can also do the unconstrained version, which is just the pseudo inverse of this H multiplied by vector or matrix representation of S. So you can recover all those things just by using that. Okay, so now how do we get these optimal streaming factorizations? Remember that we can write down expected reconstruction error. Okay, so you do some fancy tricks. I guess not that fancy. You just permute the trace around and make a couple observations. In particular, like you absorb the H dependency into a constraint. So okay, this thing is homogeneous, which means you can basically pull that H dependency into a constraint instead of actually being an element of loss. point is you can reformulate this problem in terms of basically H star H. And everything actually in our analysis is allowed to be complex, but you can think about it all as real if you want to be. So you can just formulate the problem like this. This problem is actually strictly convex over the space in positive definite matrices. You should think about that as being like analogous to 1 over x is convex if x is positive, right? So that's basically what's going on here. So this is a linearly constrained, strictly convex problem. So you can solve it, or you can straight analyze it and characterize the solutions in terms of a fixed point problem. So there's a unique solution to that optimization problem we had on the previous page, and you can express the solution as this. Basically, there's some really, really nasty, or at least in my mind, really, really nasty vector value mapping that determines the setting of your Lagrange multiplier. But once you know this, you have a pure expression for your optimizer. So as far as we know, this kind of thing hasn't been discussed before, but the problem we formulated on the previous slide actually has. And there's kind of different methods of solution, right? You can use, traditional convex optimization stuff to solve that problem too. But I'm not aware of, you can imagine this equation 13 here is also being kind of like a reparameterization of the problem in n variables instead of n squared, which we haven't. I mean, we literally just observed that like yesterday, so we haven't thought about too much about that. Like, is this thing still convex in this variable lambda? I don't know. But anyway, that actually doesn't matter that much, because you don't know if those solutions that you get are streaming solutions. But once we solve this optimization problem, kind of like in some ways, this is kind of like the technical core of our paper, you can actually just convert any solution to a streaming factorization, essentially by like computing a variant of a Cholesky factorization. So this psi you should imagine as being almost like a Cholesky factorization, except Cholesky factorization gives you like the wrong triangular structure. So we essentially show that you can map streaming solutions of this factorization problem into like lower triangular matrices, right? Which kind of makes sense, means you don't depend on any values in the future to compute the value you need in the intermediate thing. But point is that once you have any factorization, you can compute some function of H star H, where star is, this star is Hermitian conjugate, right? So like transpose and take complex conjugate over. And you'll get something that is square, positive, semi-definite, lower triangular, which has like equality in terms of H star H, like they're the same thing. Column numbers are the same, and you haven't increased your loss at all. Well, you haven't increased your loss at all for some function you can compute of this thing. Which means that if you can solve the optimization problem, you can actually get a streaming solution immediately, right? And it's very simple to compute this thing. I mean, all you need to do is compute a single Cholesky factorization basically, and a couple of integers multiplies. So at the end of the day, point being that it's actually really easy to compute these optimal streaming factorizations, assuming you can solve this problem. I didn't mention this on the previous slide, but the way that we solve the optimization problem phi is we just iterate that mapping phi, and it empirically converges. I tried for weeks to prove its convergence, or ideally to literally write down what is an expression for that fixed point. If you didn't have the geometry that we had in H, you can literally just express this as like square root of S star S. If your H were measured in Frobenius norm, for example, instead. But I never proved that those iterations converge or derived an explicit expression for that fixed point, so that irks me. But computationally, it always works. Although Brendan noticed that you actually need, in some cases, you really need float 64s because weird numerical instability issues taking measuring square root. But that's another story. Point being that it's easy to compute these streaming factorizations, literal optimal. It's just easy. It's not that hard. It's not that much computational problem. Oh, and we finally wrote down for you the matrix S that corresponds to gradient descent here. It's just this thing. It's sum. This is your prefix sum matrix, right? Because this is going to take, if you take x1 through xn, it's going to return you x1, x1 plus x2, x1 plus x3, x2 plus x3, etc. Right? Okay. So now, finally, towards the end here, empirics and efficient implementations. So, okay, as I said, we can compute these optima very easily, these streaming optima. And so we can compare with, to the best of our knowledge, of the state-of-the-art streaming prefix sum estimator, which is this Hanukkah estimator from below, and it looks a lot better, right? So the difference in expected squared error between these two is really about 4, about a factor of 4. So we measure it usually as the square root of the expected square error, the expected error, and it's about a factor of 2. But there's also an interesting point that I think we want to call your attention to here, which is the difference in kind of smoothness between these two things, because the Hanukkah estimator really, by virtue of being defined in terms of this binary tree, has some like artifacts to data structure there, which you should understand as being like, okay, if I have a node that is the top of something, I actually have like the maximal number of redundant observations of this thing in the tree. So like x1 plus x2, you have way more observations of this than like x2, for example, if you're computing everything from below, right? Because when you're trying to compute x2, you've only observed x1, which means that like you have no extra information about that. But when you're trying to compute x1 plus x2, you've observed x1 and x2 also. So you should think about that in terms of x1, my bad. But anyway, like point is that you have the different nodes in the tree, the different indices have different amounts of redundant information like embedded in the tree data structure. So you can get kind of different, your optimal estimator has different has different variance around these different estimates. There's also this question around how these implementations actually work. Like, do they work well? Like, what does an implementation of a factorized matrix look like? If you're using the Hanukkah estimator from below, you only need a logarithmically sized buffer with the correct implementation to implement the whole strategy that you want. Our factorizations naively are dense, although they have some structure that I don't understand in theory, but like they look pretty if you plot them. So since they're dense, you need this kind of linear number of operations to compute your intermediate, your estimate at time t. But if you introduce some kind of structure, if you introduce some kind of structure, there we go. This is coming back now, right? Yeah. Which is essentially like one of the things that you can really observe from looking at these matrices, that they're mostly diagonal dominant. So if you take kind of like a bunch of elements off a diagonal and you low rank factorize the rest, like the difference, you can design an algorithm which has an efficient implementation, which is kind of like comparable to the efficiency of the Hanukkah implementation, and kind of keeps most of the improvement here. So the efficient one is on the right-hand side. And the D and the R there, they parameterize, number of elements of diagonal and rank of your low-rank factorization. And those are chosen such that the memory requirements in particular, and really the computational requirements generally, are comparable to those of the Hanukkah estimator for the same dimensionality. Okay, so towards the end here, open problems and upcoming work. First, we've never trained anything with these models or with these mechanisms. So we actually don't know how good they're going to be for this purpose. Clearly, there's some expected improvements, but the effect of that smoother trajectory of the per step errors, it's really difficult to predict that. I mean, I have no principled way to predict that. We're excited to observe it because like you would really imagine that like super spiky variance thing would certainly be significantly suboptimal for like training machine learning model, but who knows? There's also these kind of generalized questions of geometry, meaning we did all this analysis in terms of a single pass algorithm, but maybe it's easier in the infrastructure to design kind of something that's multi-pass, or design something that you can kind of read ex post facto. You don't need to like enforce how far spaced apart your participations are, say. This corresponds to adjusting the geometry under consideration, as kind of I mentioned you put our sensitivity term into the constraint in the analysis that we've done, which means that like now the sensitivity term is going to have kind of a different geometry, right? You can also ask about different geometries in the target domain, right? Like measuring different notions of error that may be better for different applications. So there's this question of like, how can you define or design efficient algorithms which are essentially parameterized by these geometrical concerns? As far as I know, even in the literature on matrix factorization, this question, like the pure literature on matrix factorization, no streaming, no nothing, this question is basically wide open because everybody that's going to design an efficient algorithm, similar to us, like our fixed point formulation is essentially leads to an efficient algorithm, but like that's heavily relies on the geometry, right? But so do all the other efficient algorithms that I'm aware of. Otherwise, you have this like, you have this general convex problem and n-squared variables. It's like, okay, good luck. Actually, I mean, I have no idea how good convex solvers are today. So maybe you don't even need luck to do that. Who knows? Adaptivity. The solutions that we've all presented here, they depend on knowing the number of iterations you can compute in advance. But can you relax this requirement? And of course, now this is my pet problem. Expression for fixed point of phi. This may be really, really difficult to do, but it does offend my sensibilities to make 99% explicit, like, oh, I have total explicit representation for this thing, except I need you to tell me what this vector is. It's like, oh my God, I hate that. So, this is my pet problem. But it might be really hard. I have my old advisor, I've set him loose in this problem. So we'll see if this can be. Actually, there's an interesting connection here with, I think it's called quantum fidelity. Like the trace of phi that we presented earlier, that's the quantum fidelity of something with something. I forget what, but I asked this on Math Overflow. That's what somebody came back to me with. And that's it. That's it. Thanks everyone for all your attention. Yeah, so any questions? Nobody interrupted me.
Awesome. Thank you so much. Yeah, any questions, feel free to put something in the chat window. We can also unmute you, I believe. So maybe I'll ask a question while we're waiting. Oh, actually, there's a question I just saw, but yeah, so one question I have is if you were implementing this in practice, how would this deal with something like dropped clients? Does that affect this procedure at all? Is this robust to something like that?
It should be, because the averaged, like this is essentially a central mechanism. So the averaged thing is already computed by the time it's being fed in here.
Okay.
So like that, yeah, that's yeah, oh yeah, that's the argument that we get. I haven't thought much about whether a localized version of this like whether that's even possible, but maybe it is, who knows?
I think there was a question in the chat window, although Brendan may have answered it already. Cool.
Yes, I'll note about Brendan's answer that like that was surprising to us, and you can also make it all square. That was really both of those facts. The fact that you don't lose anything by restricting yourself to streaming factorizations or square streaming factorizations, like, is fine. Like both of those, and in some sense, that's kind of like the main result of this work is that like, oh, here's a mapping that tells you that fact immediately. I don't think I know what HFL is.
Yeah. Is it possible to apply this for HFL? What's HFL stand for?
It's hierarchical federated learning.
Wait, sorry, I missed that.
It's hierarchical federated learning.
Oh, okay, hierarchical. I guess I don't know. I guess that is. I don't know what that is still. So like, I guess I can't really say. I don't know if Brendan or Albert has knowledge about this.
Yeah, maybe you could say a little bit more about the setting and what kind of privacy guarantee you'd be looking for.
You should be able to unmute yourself, Sarwar. Okay, it seems that we are unable to unmute Sarwar.
I guess we could give a general answer as to when this is applicable. And I think the answer is that, you know, our techniques that have looked at sensitivity where each user contributes on a single round. And here you can really replace user with whatever your unit of privacy is, right? So if you wanted DP with respect to silo or some other kind of partitioning of the data, then you would need to kind of consider whatever your node, that unit of DP, call that a client. That client can participate at most once per round, and you need kind of an L2 norm bound on the magnitude of their contribution on that round. And I think with those two things, you can plug this in to kind of DPFTRL and get a DP guarantee with respect to that notion of client. And you could compute, so X in general, like the XI, that's, you can think of that as the sum or the average over all of the clients on a given round, and you could compute that in an arbitrary way. That's just so really what we focused on here is that there's some final central aggregator that executes this central DP mechanism, and you could use whatever aggregation procedure before that you wanted. So in particular, it wouldn't give you a distributed differential privacy guarantee, but you could combine this with a secure aggregation protocol or a two-party aggregation protocol or whatever to kind of compute the XI on each round. And then kind of the trusted aggregator just runs this mechanism on top of those per round contribution, per round sums or averages.
I think you already mentioned this, but is there any computational overhead then at the central server for implementing this?
There is. It's so for the for like the literally optimal versions, you know, we're thinking currently about what exactly implementations make the most sense. For the literally optimal versions, you can compute. You can either like keep a buffer that tells you something, which is going to grow linearly, or you can pay this cost computationally every round, essentially, because you can express it all in terms of like post-processing of some noise, imagine sampling once. So you could pay some linear cost and compute your literal optima, or you could pay this logarithmic cost, which is kind of analogous to the cost you pay with the existing Honecker solutions, and you keep most of the improvement that I'm having. There may be better ways to do this actually too. Like there may be better, you know, there may be ways to introduce some structure that keep even more of the thing, but you know, it's pretty close now. It's maybe like a 10% drop or something like that, maybe 5. So to pay that logarithmic cost.
Okay, got it.
Yeah, phrasing that. There's actually kind of two optimizations going on here, right? There's just computing that matrix factorization WH, which you could think about the server doing, but that's a one-time thing. That factorization is just a fixed mathematical object. So you would need to do that once per number of rounds you were going to run, just compute that matrix, right? So for example, if you knew you wanted to run training for 4,000 rounds, you need to run an optimization kind of offline before you start training to find this pair of 4,000 by 4,000 lower triangular matrices. And that's, you know, those are moderately big matrices, but that's relatively inexpensive using the fixed point techniques that Keith was talking about. And then what that actually looks like at runtime is you kind of have to apply that matrix to each coordinate of the model. So if you had a say your model had 1 million parameters, you would be keeping kind of a cumulative sum of the gradients, but you would it's actually kind of adding up the appropriate correlated noise. That's the expensive part. So you can think of having a noise vector of length 1 million for each round, and you need to compute some linear combination of, 4,000 of those 1 million dimensional noise masks. So if you do that naively, it could be moderately expensive, though with the right optimizations, it might not be too bad. But then we have some tricks in the paper that rather than needing to keep around kind of all 4,000 noise masks, you can do dramatically fewer than that.
Okay, interesting. Yeah, thanks. That was very, very helpful.
One interesting observation about the way that you kind of compute that like post-processing step at runtime is that I think we were just asking some people on our team who are like big pseudorandom number generator and like sampling like traditional statistics experts about this, because I think if you could just like sample from a Gaussian with arbitrary covariance, you would be able to avoid this problem entirely. It's like creating that weirdly, it's isotropic Gaussian that's like causing this problem. So if anyone knows how to do that, let us know.
I think we might have time for one more question. So Tiana has a question in the chat window about whether this can already handle, or you could extend this to handle optimizing over multiple passes of the data.
Yeah, that is current work, because you can pose this problem, like you can pose direct optimization over this question of like, okay, different kind of participation structures. This is kind of like adjusting the geometry of the problem under consideration. You can pose it in the same framework. I think we don't know how to compute optima as well. Or you could, there's kind of heuristics you can imagine to construct a solution that gives you, similar DP with multiple passes. It's just not known to be literally optimal in this class. So basically, I think that's the difference here. You can apply similar techniques. You're gonna get some kind of benefit. How does this relate to like the optimal? That's something that I don't know.
I see. Okay, but so that would break some of the guarantees that you had, but maybe you could still apply that to that practical scenario. Okay. Cool. Well, we'll have I think the recording up soon. And I just want to thank our speakers again, Keith especially. Thank you, Keith. And thanks everyone for joining today.